Hello, and welcome to the first edition of the tutoring videos, which is a new series we'll be trying out throughout the course of the Neuroscience block. I'm your narrator today, Moran, and the sexy Picasso-esque hands laying down these beautiful drawings is your tutor coordinator, Jonathan Chen. Today, we'll be doing a summary of some key concepts you should take away from your intro to neuroscience, and this will be focused on primarily anatomical features of cranial structures and some basics into pathology pertaining to these structures. Here, Jono has begun to lay out the 4 key lobes that gross examination of the brain is commonly recognized by. We have the frontal lobe, where reasoning, planning, and higher levels of cortical function occur, the parietal, which is associated with movement and orientation, the occipital, for visual processing, and temporal lobes, for auditory processing, speech, and memory. Then, of course, inferiorly is our brainstem, where all the functional axonal tracts for the rest of the body run, as well as being the home to respiratory and cardio centers. Posterior to that is the cerebellum, its primary role being to help refine motor functions. So those are obviously some pretty fun and important functions to have as a human being. So how then do we protect these fragile, susceptible soft tissue structures from the estranged cricket balls that might be bowled towards your head by an inexperienced and tremendously uncoordinated bowler like myself, a Canadian who doesn't know what a cricket ball looks like? Well, predominantly that's done by 2 means. As Jono is now drawing for us, and I might add what a darn tootin' fine job he's doing, it's the bony and soft tissue structures of the skull that help to protect and nourish all that fine parenchymal brain tissue. The most proximal structure to the brain is our first of 3 meningeal layers, the pia mater. Above this is our subarachnoid space, where we'll find much of the vascular structure supplying the brain. And above this is then our arachnoid mater and our dura mater. It's the invagination of these structures into the sulci and fissures of the brain that helps provide some stability and shape. The larger example of these being our falx cerebri and tentorum cerebelli. These also provide structure to the vasculature, providing our neuronal cells with all that sweet, sweet glucose that they need for thinking. In many instances, that thinking is primarily about how to get more of that sweet, sweet glucose. What I'd like you to note here is the potential spaces that Jono has highlighted for us now above and below the dura, the epidural and the subdural space. In an instance of a bleed, one important clinical distinction is which meningeal layer the blood vessel has been damaged in. The dura mater is usually tightly adhered to the bony structures of the cranium and is home to many arteries. In the instance of a bleed, however, these layers can begin to separate, creating our epidural space. Similarly, we have a subdural space between the dura and the arachnoid layer, where we primarily have venous structures, so bleeds here tend to be a little bit slower. Fortunately, the nature of the dura mater's intimate relationship with the skull helps us to distinguish with imaging what type of bleed has occurred. As Jono is illustrating now, the skull is composed of many separate pieces of bones that are fused in what we call sutures. The dura mater underneath ducts into the suture lines and forms tight adhesions, because they're pretty tight buds. One important suture to recognize is the one Jono has highlighted here between the frontal bone, temporal bone, and the greater wing sphenoid. This is called the Tyrian Suture. Its importance lies in its crappy architectural design. Our early evolution clearly didn't incur a whole lot of cricket balls, because even my weak gangly arms would be sufficient to cause a big old fracture if I bowled one into the suture right here. And what's more, this bogus hodgepodge design evolution has given us has opted to put a massive artery underneath it, called the middle meningeal artery. But Jono, my Michelangelo of partners, where exactly does that artery come from? Well, the aorta. Wow, great. Thanks, Jono. That's really helpful. Oh no, wait. I see what you're doing. Okay, good. Good. Jono has now begun to draw for us all of the vascular supply to the skull. So, off of the aorta, there's a right brachiocephalic, giving a right common carotid and a right subclavian artery. And then the second and third branches of the aorta being our left common carotid and our left subclavian. Our vertebral arteries then branch from the two subclavians, ascending in the foramina of the cervical vertebra, if you can remember that, and then anastomose in the midline to form the basilar artery. This vertebro-basilar system gives our first major arteries to the CNS. There's our anterior spinal artery, which descends down the spinal cord, and there's our posterior inferior, our anterior inferior, and our superior cerebellar arteries, all of which supply portions of the brainstem and the cerebellum. Lastly, there's our posterior cerebral artery, which ascends to supply structures in the brain. Importantly, we also have a separate supply of blood that comes from our common carotids. From the common carotid is the internal and external, which respectively travel internally into the cranium and externally outside of the cranium. The internal carotid provides the anterior cerebral artery, and in doing so becomes the middle cerebral artery. These two major arterial systems anastomose to form the circle of Willis, which we'll go over in more detail in later videos. But for now, let's go back down to the external carotid, because I'm keen to know just what's going on down there, Jono. Right, now, there are many branches of the external carotid, which primarily supplies structures of the face, but branching off this sneaky little maxillary artery in the substance of the parotid gland is our middle meningeal artery. There she is. Now this tricky little bugger sneaks its way back into the cranium through the foramen spinosum and begins to course its way along the skull, eventually immediately posterior to the Tyrian suture we saw before that is bound to bust open when it gets slapped by a cricket ball. Now that sounds like bad news. So what exactly do we see on CT when we have a traumatic injury to one of the vessels around the brain? Here, Jono has begun to trace out for us a transverse section through the head, similar to something you might see on CT when investigating a bleed in the cranium. In the first example, we see the bleed has an ellipsoid shape. Now, remember how I said the dura is super tight buds with the skull, and that they like to pop it and lock it in those sutures? Well, consequently, that means the bleed isn't able to extend beyond those sutures, or at least the intact ones, which is why they present with that ellipsoid shape that they do. In contrast, a bleed from an injury to a vessel immediately below the dura, in the subdural space, which you'll recall is more commonly a vein, won't be confined to the tight-knit relationship of the dura. The arachnoid and the skull aren't really homies, so the blood just extends along the surface of the arachnoid mater and the dura mater, creating the crescent-like shape we see here. And that's all we have for you today, ladies and gentlemen. Thank you very much for sitting in on us throughout this first of our video lecture series that we'll be trying out for the Neuroscience course block, and I hope you all have a great week too.